Engineering design, management of change, establishing a structured, accountable framework for modifications in complex industrial systems. Senior technical authority, the gatekeeper of integrity and oversight in engineering change. The Senior Technical Authority, HIE, serves as the highest level technical custodian within the Management of Change (MOC) process. Their role is not only to review and authorize engineering changes, but to ensure that such changes uphold the safety, integrity, and long-term reliability of the asset or facility. The STA provides strategic technical direction, cross-discipline coordination, and final adjudication on engineering judgment, especially in situations involving uncertainty, trade-offs, or competing priorities. They are the final internal authority on whether a modification aligns with engineering principles, safety case obligations, and company standards. Key responsibilities of the Senior Technical Authority include classification and technical direction. At the initiation stage, the STA determines whether a proposed change is a full engineering modification, configuration change, or maintenance modification, the appropriate level of review and documentation required based on risk and complexity, which departments or technical disciplines need to be consulted during evaluation, review and oversight of modification proposals. The STA thoroughly evaluates all modification submissions to ensure justification is sound and based on technical, safety, or operational rationale. The proposed change does not compromise the facility's safety case or design integrity. All potential consequences have been considered and mitigated. Judgment on ambiguities and trade-offs. When multiple implementation options exist or when justification is borderline, the STA guides the engineering team in comparative assessment of options, initiates further study, analysis, or risk assessment as needed, balances economic, operational, and technical considerations to determine the best path forward, safety review, and risk determination. The STA determines whether a formal safety review, e.g. HAZOP, QRA, SEAL assessment, is required and ensures that all identified risks are evaluated and addressed. Safety-critical elements are not undermined by the change. Recommendations from safety studies are tracked and incorporated. Final technical approval and sign-off. Prior to implementation, the STA provides final review and approval of the engineered solution, confirming that all stakeholder inputs have been addressed. Sign-off on MOC documentation, drawings, and procedural updates. A formal decision on whether the modification may proceed to field implementation. Post-implementation review. After a defined operational period, typically 3 months, the STA reviews the effectiveness and impact of the modification, determines whether the change should be formally closed out or further adjusted, confirms that all records and documentation reflect the final implemented state. Regulatory and organizational interface. Where needed, the STA may liaise with external regulatory bodies, certification authorities, or internal audit teams, escalate decisions to senior management in the case of critical or high-impact modifications, ensure alignment with national and international engineering standards. As the technical conscience of the organization, the STA ensures that every modification is held to the highest standards of engineering rigor. Their involvement reinforces trust in the MOC process, not just internally, but also with regulators, partners, and the public. By acting as both guardian and guide, the STA anchors the entire system to its core purpose, ensuring safe, reliable, and justified change. Engineering design, management of change. Establishing a structured, accountable framework for modifications in complex industrial systems. Mechanical Structural Technical Authority, safeguarding physical integrity across design and execution. The Mechanical Structural Technical Authority, MSTA, holds a critical role in the management of change process by ensuring that all mechanical and structural aspects of a proposed modification uphold engineering integrity, comply with standards, and maintain long-term operability. Whether a change involves pipe rerouting, support steelwork, pressure systems, or skid structures, the MSTA ensures that design alterations do not introduce unanticipated risks, such as added weight, corrosion vulnerabilities, or mechanical overstress. Their role blends detailed engineering validation with a vigilant focus on maintainability and durability. Key responsibilities of the Mechanical Structural Technical Authority include review of mechanical and structural scope. The MSTA examines all proposed modifications that involve pipework and vessel alterations, equipment foundations, supports, or access structures, mechanical interfaces including bolts, gaskets, flanges, and sealing systems, modifications to skids, structural frames, platforms, or walkways, assessment of technical integrity. Each modification is scrutinized to ensure compliance with applicable mechanical codes, stress criteria, and material specifications, no compromise to structural stability, load-bearing capacity, or fatigue life, impact on adjacent systems such as dynamic loads from rotating machinery or added weight to existing supports, weight control and load management. The MSTA evaluates modifications for weight impact by verifying that new loads are within acceptable limits for decks, supports, and transport interfaces, ensuring that weight changes are tracked within the facility's weight control program, reviewing implications for structural lifting and handling during construction or maintenance, corrosion risk evaluation. The MSTA anticipates and mitigates corrosion risks by reviewing changes that introduce dead legs, flow stagnation zones, or inaccessible coatings, assessing material compatibility and environmental exposure conditions, coordinating with process and inspection teams on design details that affect corrosion, monitoring, and maintenance. Standards compliance and best practice. All mechanical and structural modifications must adhere to organizational, national, and international engineering standards, use approved material grades, fabrication practices, and assembly techniques, be designed for maintainability, safety access, and equipment longevity. Technical commentary and documentation. The MSTA contributes structured feedback during the MOSI review process by raising formal comments in review cycles with clear technical justification, avoiding speculative or opinion-based design inputs not grounded in engineering analysis, ensuring that all relevant records, equipment registers, inspection plans, drawings are updated accurately. Interface with construction and field implementation. During implementation planning, the MSTA verifies constructability and erection methodology, ensures appropriate lifting plans, field weld details, and support modifications are reviewed, confirms that mechanical isolation, hydrotesting, and reinstatement are addressed in the work pack. By overseeing these dimensions of every mechanical or structural change, the MSTA plays a fundamental role in protecting the physical backbone of engineered systems. Their diligence ensures that changes introduced for operational or process benefit do not inadvertently degrade mechanical reliability or structural safety. The MSTA's contribution to the MOFI process is grounded in a deep understanding of how design translates into real-world performance, making them a critical link between engineered intent and long-term operational integrity. Engineering design, management of change, establishing a structured, accountable framework for modifications in complex industrial systems. Instrument Electrical Technical Authority, ensuring control system integrity and electrical safety in all modifications. The Instrument Electrical Technical Authority, IETA, plays a pivotal role in the management of change MOF process by safeguarding the integrity, functionality, and safety of instrumentation and electrical systems. Their responsibilities span the evaluation of modifications to power distribution, control logic, field instrumentation, and safety-critical systems, ensuring that changes do not introduce new risks or compromise the operability of automation and protection layers. In high-reliability environments where process safety, signal integrity, and power continuity are vital, the IA provides the necessary expertise to ensure that every change is technically sound, electrically safe, and fully traceable. Key responsibilities of the Instrument Electrical Technical Authority include evaluation of instrumentation and control scope. The IA reviews all proposed modifications that affect field instruments, e.g. transmitters, control valves, sensors, programmable logic controllers, PLCs, distributed control systems, DCS, emergency shutdown systems, ESD, and fire and gas systems, control logic, trip settings, interlocks, alarms, and analog digital signal pathways, instrument loop integrity, grounding, shielding, and cable routing. Electrical systems review modifications involving electrical infrastructure are assessed for compliance with voltage ratings, short circuit levels, and protective device coordination. impacts on single-line diagrams, motor control centers, power panels, and load schedules, adherence to hazardous area classification standards and proper earthing bonding, power redundancy, backup supply, and emergency shutdown implications, software and logic change validation. For changes affecting programmable systems, the IETA ensures logic modifications are backed by proper design rationale and change documentation. Software backups are secured and version controlled. Testing, simulation, and verification are conducted before deployment. Signal response and fail-safe behavior are validated against design specifications. Compliance with standards and specifications. All instrument and electrical changes must comply with internal engineering standards and approved instrument electrical specifications, national and international codes, e.g. IEC, ATEX, or equivalent, system-level documentation requirements including loop drawings, cause and effect charts, and interlock matrices, impact on safety and reliability. The IETA assesses whether a modification affects the safety integrity level (CL) of instrumented systems, introduces risks of spurious trips or degraded fail-safe performance, compromises electrical load balance, insulation, or arc flash protection, documentation, and data integrity. As part of the MOSI review, the IETA ensures updates to instrument data sheets, loop diagrams, and I/O lists, electrical single-line diagrams and cable schedules, program backups, tag registers and configuration records, fire and gas maps, and power system schematics, technical commentary and sign-off. During the review process, the IETA provides structured feedback and raises technical queries as required, avoids speculative or incomplete judgments, instead grounding comments in verifiable engineering criteria, confirms closure of all comments before approving the modification. Field Implementation Interface. For site work, the IETA ensures proper pre-commissioning, loop checks, insulation tests, and functional verification. Safe isolation, energization, and lockout-tagout procedures are in place, that the work is executed by qualified personnel in accordance with electrical safety standards. Through their oversight, the IETA ensures that modifications enhance, rather than erode, the reliability, functionality, and safety of the control and power systems that underpin the facility. Their vigilance ensures that even a minor logic update or instrument replacement is properly engineered, tested, and documented within a secure and traceable framework. In a digitalized, automated, and high-risk environment, the IETA's role is indispensable to engineering assurance and operational continuity. Engineering design, management of change, establishing a structured, accountable framework for modifications in complex industrial systems. Process Technical Authority, protecting process safety, operability, and system performance across all modifications. The Process Technical Authority, PTA, plays a central role in the management of change MOSI process by ensuring that all proposed modifications align with fundamental process engineering principles, preserve system operability, and do not compromise process safety. Whether the change involves equipment sizing, flow paths, chemical handling, or thermal balances, the PTA ensures that the entire system's behavior, under all operating conditions, is fully understood and respected. Their role demands deep technical judgment, a holistic view of the process network, and rigorous attention to detail. The PTA acts as the steward of mass, energy, and process integrity. Key responsibilities of the Process Technical Authority include evaluation of process scope and impact. The PTA reviews all modifications affecting piping and instrumentation diagrams, P&IDs, process flow diagrams, PFDs, and heat and material balances, operating conditions such as pressures, temperatures, flows, and compositions, equipment function and rating, e.g. separators, exchangers, reactors, pumps, compressors, introduction of new process chemicals or utilities, assessment of process risk and integrity. The PTA evaluates whether the change alters process dynamics or introduces instability under startup, shutdown, or upset conditions, introduces risks such as overpressure, thermal runaway, reverse flow, or accumulation of hazardous inventory, affects control strategy, interlock logic, or process alarms, requires updates to the safety case, risk register, or hazardous area classification, review of system-wide implications. Beyond the local modification, the PTA considers downstream and upstream impacts on connected systems, heat integration and utility balances, e.g. steam, fuel gas, cooling water, interface effects with blending, flaring, storage, and product quality systems, the need for updated simulations, hydraulic calculations, or flare load evaluations, verification of design and operating margins. The PTA ensures process conditions remain within the allowable design envelope of equipment, relief systems are adequate and correctly sized for new scenarios, normal and abnormal operating procedures remain valid or are updated, standards, compliance, and best practice modifications are checked against company standards and industry design codes, e.g. API, ASME, IEC. Best practices for process reliability, safety, and environmental performance. Lessons learned from past incidents or performance issues, process documentation and registers. The PTA ensures that all changes are reflected in updated P&IDs and PFDs, process simulation models and control narratives, hazardous area classification drawings and safety-related device registers, chemical inventories and operating envelopes, structured review and technical commentary. During the MOSI process, the PTA provides technically sound and traceable feedback, avoids personal or unsupported opinions, grounding comments in quantitative and qualitative engineering analysis, confirms that all process risks and scenarios have been accounted for, support during implementation and commissioning. The PTA participates in pre-startup safety reviews, PSSR, and functional testing of process control and safeguard systems, verification of sampling, flushing, and commissioning procedures, updating of standard operating procedures and training material for operators. By carefully reviewing the process implications of each proposed change, the PTA ensures that modifications do not erode plant performance or process safety. Their work preserves the stability, efficiency, and robustness of systems that often operate under extreme conditions and tight tolerances. In essence, the PTA acts as the engineering conscience of process design, ensuring that every modification enhances functionality while protecting what matters most: safety, reliability, and control. Engineering design, management of change, establishing a structured, accountable framework for modifications in complex industrial systems. Maintenance authority, preserving reliability, serviceability, and life cycle continuity in every modification. The Maintenance Authority, MA, is a vital stakeholder in the Management of Change, MOC, process, responsible for ensuring that every proposed modification remains compatible with long-term maintainability, asset reliability, and maintenance system integrity. Whether the change involves mechanical components, instrumentation, electrical systems, or software, the MA validates that it can be properly serviced, scheduled, and sustained throughout its life cycle. The MA's involvement ensures that no modification creates a maintenance burden, introduces accessibility issues, or disrupts preventive or predictive routines. Their focus is on operational continuity, ensuring that the equipment, once modified, remains manageable, safe, and efficient over time. Key responsibilities of the Maintenance Authority include review of maintainability impacts. The MA assesses whether the proposed change affects equipment access for inspection, servicing, or replacement, routine maintenance intervals or required procedures, clearances for lifting, isolation, flushing, or calibration activities, long-term availability of spares and tools, integration with maintenance management systems. All approved modifications must be reflected in the Computerized Maintenance Management System, CMMS. The MA ensures new equipment or systems are registered with accurate asset tags and metadata. Updated maintenance intervals, task procedures, and checklists are revised. Maintenance planning and scheduling are aligned with the operational criticality of the asset. Assessment of reliability and operational exposure. The MA evaluates historical performance and failure modes of similar systems or components, risk of reduced reliability due to the modification, e.g. complex valve changes, exotic materials, non-standard seals, impacts on mean time between failures, MTBF, or repair times, MTTR, requirements for condition monitoring, redundancy, or spare strategy adjustments, standards, compliance, and execution feasibility. The MA ensures that all modifications conform to established maintenance standards and manufacturer recommendations. Field implementation is supported by job plans, tooling, and skill availability. Isolation requirements for electrical, mechanical, and instrument loops are properly defined and executable. Documentation and feedback loops. The MA is responsible for updating and validating equipment maintenance manuals, service procedures, and inspection forms, calibration records and test certificates for instrumentation changes, maintenance strategy documents, and criticality assessments for newly introduced systems, structured review and risk commentary. During MOSI review cycles, the MA provides practical feedback grounded in field experience and asset history, identifies potential maintenance bottlenecks, safety exposures, or access limitations, ensures that proposed changes are not only maintainable, but maintainable efficiently, interface with field teams and contractors. The MA supports implementation by verifying installation methods and confirming post-modification maintenance readiness, coordinating with field technicians to validate service accessibility and ergonomic concerns. Ensuring operational readiness checks include maintenance diagnostics and startup routines. By anchoring each modification in practical lifecycle considerations, the MA ensures that changes not only perform as designed, but can also be sustained with minimal disruption and maximum uptime. Their perspective brings the long view to engineering change, where success is measured not just in safe startup, but in years of trouble-free operation. The MA serves as the voice of maintainability in the MOSI process, championing an approach where engineering improvements never come at the cost of long-term serviceability, reliability, or field practicality.